I mentioned, of course, that there is a big focus from the Brain Initiative on human neuroimaging and on developing novel techniques to modulate activity within the human brain. And although our focus is on basic science and although our focus is on technology development, this human component is important because as quickly as we can, we want to try to allow for the translation of these technologies into clinically relevant projects. And these devices can record activity, determine with an algorithm when that individual is about to make a movement, and then turn on the stimulation that reduces the tremor. These devices have already been implanted in a handful of patients and really are working quite well. And this is important for several reasons. Number one, that the constant stimulation that's present in these devices does cause side effects. So obviously, if you only have the stimulation running when you need it, then those side effects are reduced. It also improves the battery life of the device. And of course, changing out the battery requires a surgical procedure, a minor one, but a surgical procedure nonetheless.
Each electrode is inserted into your head via tiny threads that are roughly 5 micrometers thick. They're around 10 times smaller than a human hair and contain 32 electrodes each. It's roughly the same size as a neuron, which is a good idea. As the robot inserts each thread one by one, at the end, there could eventually be up to 10,000 of these electrodes inside your head, each responsible for recording separate neurons which can later on be analyzed. But not only can they read data from your brain, they can also input data as well. It's a two-way street. It's sort of like being able to upload and download things from your brain. Brain implants aren't exactly new either, though. They go as far back as the 1950s. Empathy is no longer unrealistic. The electrode implants that detect neural signals wirelessly transmit their data back to the small computer behind your ear. So, the idea of transferring data back and forth between these devices is relatively simple to imagine. And because the electrodes can both read and write data, you could theoretically communicate back and forth between people who also have Neuralink implants. Now at the moment, the technology isn't exactly close to making this happen. Maybe a word or two. But in theory, and with enough improvements, it is possible for high bandwidth communication between two people using nothing but their minds. It may be an aggressive approach, as Elon tends to take, but you can see Neuralink implants in human patients by the end of this year.
And what we'd like to do is to go beyond just developing correlations between, say, a pattern of self-firing and the behavior, but actually demonstrate causality, that firing pattern actually does give rise to that behavior. And we can do that now if we can get enough data on how the neural circuit is behaving, develop a model that links the neural circuit activity and its patterns of activity to the behavior, and then actually intervene and change the neural firing pattern and predict what that will do to behavior in an animal, for instance. That gets us past just correlation, but gets us to really the link between the causal nature of the neural activity and the behavior.